Okay, so today we would like to talk about, it's just the question in last week. Yeah, it's the attendance problem in linear algebra. So the first one is this one. We would like to apply Gram-Schmidt to change the linear independent set into an orthonormal basis of R2, and in R3 space we would like to change it into an orthonormal basis of R3. But here you could see that for these two sets, for the vector, we could call it x1, x2, and for this vector, what's the difference? Actually, here is 2 by 1 vector, 2 by 1 vector, it's 3 by 1, 3 by 1. But each of them, for these two vectors, the third component are 0. Otherwise, it's the same, 1, 1. 1, 1 is 1, 1, negative 1, 2, negative 1, 2. Yeah, so when you apply Gram-Schmidt process, you will see, once you solve this question, for this question, our first step or second step, it will be similar. Just in third component, we add 0, then you could get the same process. Okay, yeah, the difference just here, we add 1, 0, 10, 1, 0. For the third component, we add 0. So in the process, we do the same thing. Anyway, so let's see the first question. The first question we have, it's easy to check. Actually, it's easy to check. S1 is 2, 1, 1, negative 1, 2. Its determinant equals 2 subtract negative 1. So 3 is non-zero. It means that this set is linear independent. So it's a linear independent set in a plane. And we could use Gram-Schmidt to change it into an orthonormal basis. So what's our first step? For our first step, we have, for the question 1, I have already sent you the solution, so you could just tell you some process or idea in its proof. Okay, so first step, we consider unit vector u1. U1 is this one, x1, because for orthonormal basis, it should be for the set u1, for the vector u1, it should be unit vector. If it's orthonormal basis, it should be unit vector. So our first vector is, we fix x1, we start from x1, then we should divide by its length. Okay, of course you could start by x2, but here we just start by x1. So first vector u1 is 10, but you should know x1 is length, and it's equal to square root of square in each component their square, and their sum, so it's square root of 2. And then from this one you could know, just divide by square root of 2, divide by square root of 2. So indeed, u1 is this vector, and indeed it's a unit vector. In the second step, we have a vector u1. Now, for the vector s2, originally in the plane, we have a plane. We have the plane, xy plane. Yeah, it's xy plane. And originally we have a vector x1. We have vector x2. Sorry, originally we have vector s2, s1. So original vector s1 is over here. It's our original vector. And the second vector is x2. So second vector is x2. Original vector is s1 is here. Second vector is s2. And then we want to construct by Gram-Schmidt, we want to construct a vector which is orthogonal to s1. So we consider this one. Consider its projection. So for this vector, it's the projection p2, p1. Now, what's the projection? We call it projection of x2 onto x1. Projection of s2 onto s1. And the vector what we want to construct is this one. Here we can say s2 subtract p1, this vector. Here is s2, here is p1, so this direction is s2 subtract p1. And then of course we should divide by its length. But before that, what's the vector projection p1? Its formula is x2. Originally we have it's onto x1, so it has the same direction as s1. But s1 is also has the same direction as U1. So our formula is this one, S2U1, the inner product has U1. And U1 is this one, so just to check S2U1, negative 1, 2, 1 over square root of 2, 1 over square root of 2. Its inner product has 1 over square root of 2, 1 over square root of 2. Just check it. And this 10 is equal to negative 1 over square root of 2 plus 2 over square root of 2. So it's equal to 1 over square root of 2. And multiply by this 10, so each 10 you can get 1/2. This one. So it's our projection P1. But we want to know S2 subtract P1. So S2 subtract P1 is S2 subtract P1. So first 10 negative 1 subtract 1/2. So it's negative 3/2. And 2 subtract 1/2. So it's 3/2. This one. So now you could see that, but we should divide by its length because it should be orthonormal basis. It means each vector is univector. So you should divide by its length. So its length S2 subtract P1 its length equals square root of negative 3/2 is square plus 3/2 is square. Yeah, and you could count it. You could check it. It's equal to 3 over square root of 2. Yeah. So finally, our U2 is S2 subtract P1 divided by its length. So finally, it's equal to S divided by its length. So this divided by its length means multiply by its reciprocal. So multiply by its reciprocal, then you could get negative. Just some computation, then you could get it's equal to negative 1 over square root of 2. 1 over square root of 2. Yeah. So our U1 vector is this one, and the U2 vector is this one. And it's easy to see they are orthogonal indeed. And each of them are univector. So that's why we say use the Gram-Schmidt to change it into orthogonal basis. And yeah, so in our argument, of course they should be orthogonal. Otherwise, if orthonormal basis. Otherwise, how to know its orthogonal basis? As we say in previous section 5.5. If you want to show these two vectors are orthogonal basis. These two vectors are orthogonal basis. First one, you should show that because it's in R2 space and we have two vectors, so you just need to show it's orthonormal. You just need to show it's orthonormal set in R2. And the orthonormal set means that uni orthogonal vector. Orthogonal vectors, they are orthogonal and each of them are univector. So you just need to show U1 is length equals U2 is length equals 1. And the U1, U2, their inner product equals 0. Yeah. Otherwise, you also could show it in this way. Put the U1 in the first column and put the U2 in the second column. Then to show it is orthogonal matrix. Right? We have two ways to show that they are orthogonal basis. But if you apply Gram-Schmidt process for the result, of course it should be orthonormal set. So you could skip this one. Just in this case, if I want you to show it's orthonormal, then you should use this way or this way. Okay, so now let's see second one. And for second result, for second question, we still have the same process. I mean, we denote it by S1, S2, S3. And what's the relation? What's the difference? Just insert component with A0. Insert component with A0. So we still have the U1 vector, and we still divide its node, and it has the same result. I mean, it's 1 over square root of 2, 1 over square root of 2. But insert component is 0, right? It's 0. So, and after that, we still have the vector projection of S2 onto S1. And each time we could check it, each time just insert component with A0. Just insert component with A0. This one. And S2 subtract P1 is negative 3/2, 0. This one. So U2 is divided by its length. So it's negative 1 over square root of 2, 1 over square root of 2, 0. Just in third component, we add 0. This one. So we still have U1, we still have U2. Okay? But now we want to know U3. U3, but now it becomes a little complicated. I mean, here, how to get projection of x2? Projection of x2 onto s1. So we just have a vector, and we fix the vector x1, this one or this one, and we consider the vector s2, consider its projection onto s1, right? Consider its projection onto s1. But now for the third vector s3, for its previous vectors, we have two vectors, so we should consider its projection onto their spanning set, right? So here is this one. Indeed, now we have a spanning set. It's a span by x1, s2. But span by s1, s2 also equals span by u1, u2. Yeah, it's the result we have shown we have introduced in class. And now we have a vector s3. And one could consider its projection. Yeah, its projection. And the projection is here. The projection. Yeah, projection. But for its projection onto the spanning set of S1 and S2. Probably S1 is here. Probably S2 is here. Right? So you could not just consider projection onto S1 or projection onto S2. You should consider projection onto spanning set of S1 and S2. So how to consider projection onto S1 and S2? So actually in X1 we have some component. In X2 we have some component. And our formula is this one. P2 is, and this one here is some similar formula. Here is the projection of S2 onto X1. So S2 U1 inner product has U1. Now projection onto spanning set of S1, S2, but we still have this part. So that's why we say it's S3, the vector S3. U1 inner product has U1. We have this part. It's something like in this direction. In this direction we have some component. In this direction we have some component. Okay, we have some component in this direction, and we have some component in this direction, S2. So it's the component in the direction of S1. And by you should plus S3, U2, inner product has U2. And it's this part is component. This part S3, U2 is the component here. S3, U1 is the component here. Okay, yeah, and after that, just apply for this formula. And you should know S3 subtract P2, its length. You should count this one. You should calculate this vector, and consider its length. And here we could check it. I mean, write down. Actually, we could write down a solution directly. X3 is this vector, and the U1 is this vector. U2 is this vector. So once you check it, you will see it's equal to 1, 1, 0. 1, 1, 0. So S3 subtract U2, S3 P2. S3 subtract P2 is exactly 0, 0, 1. 0, 0, 1. For this part, just some calculation, you will see it's this one. And for this one, it's easy to see S3 subtract P2, its length is 1. Square root of 0 square plus 0 square plus 1 square, so it's 1. So finally, U3 is S3 subtract P2 divided by its length. So it's equal to 0, 0, 1. Divided by its length. By its length is 1. So finally, U3 vector is this one. U3, and you could see that indeed. You could see that for these three vectors, U1, U2, U3, indeed they are also normal basis. Okay, they are also normal basis. Yeah, it's the first question. It's the question on Monday. It's the question on Monday. Yeah, in linear algebra. Okay. So when we consider the projection of P2 projection onto spanning set of S1, S2, we have two components. Yeah, right? One component is in the direction of S1, another component is in the direction of S2. So we have two components. Here is related to S1, here is related to the direction vector S2. Okay? Yeah, so now I tell you the second question. It's the problem on Wednesday. It's about eigenvalue of matrix. Eigenvalue of a matrix A. Okay, so now we have a matrix A, 6, negative 1, 3, 2. So we want to consider two results. Find eigenvalue. Find eigenvalues lambda 1, lambda 2 of A. Second one is find eigenspace. Corresponding find eigenspace of A. Corresponding to each lambda, each eigenvalue. Corresponding to each eigenvalue. Okay, so now let's see how to solve it. It will, of course, it will be similar as the problem in class. So now, if you want to find its eigenvalue, as we say first step, just consider its characteristic polynomial. Anyway, just write down this. Determine A subtrate lambda I. But you should know the notation. Determinant, of course, we know that it's the determinant. A subtrate lambda I. A is the matrix 6, negative 1, 3, 2. Lambda I, what's lambda I? I is identity matrix. So identity matrix is 1, 0, 0, 1. But we should multiply by some scalar lambda. So it becomes lambda 0, lambda times 1, lambda times 0, lambda times 0, lambda times 1. This one. So it's subtrate lambda 0, 0, lambda. This one. Determine A subtrate lambda means this one. So once you compute several examples, you will see what does it mean. Determine A subtrate lambda. Just in diagonal entry, we should subtrate lambda. Otherwise, just put it down because you should subtract 0, and we do nothing. So it's this matrix. This matrix is determinant. And its determinant, 2 by 2 matrix, its determinant just 2, 6 subtrate lambda, 2 subtrate lambda, subtrate negative 1 times 3. This one. And here is subtrate negative 3, so it becomes positive 3, plus 3. And here is 6, 12, subtrate 2 lambda, use distribution, 12 subtrate 2 lambda, subtrate 6 lambda, plus lambda square, plus 3. This one. And what's this? It's exactly here in subtrate 8 lambda. So it's lambda square subtrate 8 lambda, plus 12 plus 3. So it's plus 15. Okay? And of course, you could directly lay B0 to get its root. Of course, yeah. Okay, yeah. I have already given you the solution, so I think we could skip this step. So we should figure out its solution. For this one, not this 10. I mean, you should lay B0 to find. You should lay B0 to find its root. You should lay B0. In this part, then determinant A subtrate lambda I B0 to find its root. Okay. Our argument is this one. Let determine A subtrate lambda I equals 0 to find its root. So we lay B0 to find its root. But here you should use cross measure, right? Here we are lambda, and A comes from here. We could consider 3 times 5. So here is lambda 3 5 in negative, so it becomes subtract 3 lambda subtract 5 lambda, so it's subtract 8 lambda. Yeah, so it's equal to 3 subtract lambda subtract 3 lambda subtract 5. This one. So indeed, lambda equals 3 and 5. Lambda equals 3 and 5. So we have two eigenvalues. Indeed, we have two eigenvalues. So of course, you could let lambda 1 be 3 or lambda 1 be 5. That's fine. Just without losing of generality, we let lambda 1 be 3, 5 be lambda 2 be 5. Okay? Yeah. Okay, so first question is solution is 3 and 5. 3 and 5. And the second question, find eigenspace. And why do we consider eigenspace? As we say, yeah, we should know the eigenvalue, and we also need to know eigenvector. But as we say, eigenvector, if it's eigenvector, then if V is the eigenvector, eigenvector of A corresponding to eigenvalue lambda, it means that AV equals lambda V. Then what can we say? Once you multiply by any scalar, for example 2V, it's also eigenvector of A corresponding to lambda. If you multiply negative 3, it's also eigenvector. So actually, if it's eigenvector, you could multiply any scalar. So it becomes a space. So now actually we consider eigenspace. Okay, and eigenspace means this equation holds. So in other words, it means that we could move it to a left-hand side for the scalar. So it's A, and each of them have the vector V, so we could take separate. I mean, for the common vector, we could put it in the right-hand side. I mean, originally we have this term, and we can get A subtract lambda I V equals 0. So actually it means that if you want to know the eigenspace or eigenvector of V, you should consider A subtract lambda is solution set. It's a solution set. Yeah. For the detail, you could check it in our class. The argument in our class. Anyway, so if you want to know eigenspace, you should figure out A subtract lambda is its null space. In other words, you should figure out A subtract lambda is solution set. A subtract lambda x equals 0 is solution set. Okay, so we have two eigenvalues. For example, first one is 3. Then we should consider A subtract lambda I. So A subtract 3i. A subtract lambda 1i. So it's A subtract 3i. So what's this? As we said, if you subtract some lambda, means that in diagonal entry we should subtract the scalar 3. So it's 6 subtract 3, 2 subtract 3, negative 1, 3, this one. And it's equal to 3, negative 1, 3, negative 1, this matrix. So we want to find eigenspace. It means that we want to figure out its null space. This matrix is null space. It also means we should figure out A0 is solution set. I mean, 3, negative 1, 3, negative 1, 0, 0 is solution set. The solution set of this matrix. And here, for first row, second row, they are the same. So you could cancel it, right? 3, negative 1, 0, 0, 0. So indeed, what do we have? It means that 3x1 subtract x2 equals 0. And move it to right hand side, so it means that x2 equals 3x1. So indeed, what can we say? It's null space or eigenspace, or it's eigenspace. Originally we say it's null space. But it also means the eigenspace of A corresponding to eigenvalue 3. It's exactly this one, x1 keep it, s2 is 3x1. And here s1 could be any real number. So first eigenspace is this one. It's our eigenspace. And the second one, lambda 2 equals 5. So A subtract lambda 2i. It's A subtract 5i. So it's 6 subtract 5, negative 1, 3. Just diagonal entry, we should subtract 5. 2 subtract 5. So it's 1, negative 1, 3, negative 3. This one. And again, consider its null set means that consider A0 is solution set. So it's 1, -1, 3, -3, 0, 0 is solution set. And you could see that 1, 3, so we could use it to cancel this one. -3 to cancel this one. So finally you will have 1, -1, 0, 0, 0, 0, 0, 0, 0. This one. And again here we denote it by S1, S2. So it means that S1 subtract S2 equals 0. And it means that X2 equals S1. So what's the solution say? So the solution, the null space A subtract 5i is exactly the solution set of A0. So it's exactly x1, x2, s2 equals s1. So it's this one. S1 could be any real number. This one. So for these two subspace, it's the eigenspace. It's the eigenspace of A. But for this one, it's eigenspace of A corresponding to eigenvalue 3. It's the eigenspace of A corresponding to eigenvalue 5. Okay? It's about the eigenspace. And then how about the eigenvector? Eigenvector, for example, here you could choose 1, for example, 1, 3, or 2, 6, or -1, -3. You could check all of them are the eigenvector of A corresponding to lambda 1. It means that if you check the equation AV, this one, if we denote it by, okay, for example, we choose check this one. Here our matrix A, 6, -1, 3, 2, V is 1, 3. It's equal to 6 subtract 3, 3 subtract 6. So it's 3, -3. Here is our A, V. Denote our V. And here lambda 1 times V. So it's 3 times 1, 3. So it's 3. Let me see. Here is 1, 3, 1, 9, 6. B is 1, 3. B is 1, 3. Yeah, 1, 3, so it's 6 subtract 3. 3 plus 3 plus 6, so it's 9. Yeah. And then again, of course, they are the same. So indeed, this vector is the eigenvector. And if you check, it's also eigenvector of A, corresponding to eigenvalue 3. It's the eigenvector of A, corresponding to eigenvector of 3. And for this one, you also could figure out the eigenvector, for example, 1, 1, 2, 2, and so on. Right? But it's the eigenvector of A corresponding to lambda equals 5. Okay? Lambda equals 5. Not this eigenvalue. Okay. Yeah, that's all.